Illuminating the Cosmic Microwave Background, a comparative analysis of traditional cosmology and the unified theory of U by L.S. Larkey. The cosmic microwave background, CMB radiation, a faint glow permeating the universe, has long been hailed as the afterglow of the Big Bang. This view, central to traditional cosmology, depicts the CMB as a snapshot of the early universe. Yet the unified theory of U offers a revolutionary perspective that reinterprets the origins of the CMB, attributing it to the primordial interplay between the subtle magnetic field, SMF, and the relative vacuum of space, RVS. This analysis delves into both theories, emphasizing the profound insights offered by the unified theory of U. Traditional view, the afterglow of the Big Bang. The prevailing cosmological model posits that the CMB is the remnant radiation from the Big Bang, dating back approximately 13.8 billion years. As the universe expanded and cooled, it reached a critical point where protons and electrons combined to form neutral hydrogen atoms, making the universe transparent to radiation. This epoch, known as recombination, occurred about 380,000 years after the Big Bang. Evidence. The CMB is observed as an almost uniform background radiation, with a temperature of around 2.725 Kelvin. It displays tiny temperature fluctuations or anisotropies, which correspond to density variations in the early universe. These fluctuations provide a snapshot of the universe at the moment of recombination, offering valuable information about its initial conditions, composition, and evolution. Implications. 1. Structure formation. The anisotropies in the CMB are considered the seeds of large-scale structures like galaxies and galaxy clusters. 1. Cosmic inflation. The uniformity of the CMB supports the theory of cosmic inflation, a rapid expansion that smoothed out irregularities. 1. Standard model of cosmology. The CMB underpins the LCDM, lambda cold dark matter model, which describes the universe's composition, including dark energy and dark matter. Unified theory of U, the primordial SMF and RVS interaction. Foundation. The unified theory of U challenges the traditional view, proposing that the CMB originates from the initial interactions between the primordial subtle magnetic field, SMF, and the nascent relative vacuum of space, RVS. This theory suggests that the early universe was characterized by intense dynamic interactions between these two fundamental components, leaving behind the faint imprint we observe as the CMB. Evidence. While traditional cosmology attributes the CMB to the Big Bang and recombination, the unified theory of U posits that the SMF and RVS interactions created conditions that produced the observed background radiation. The near uniformity and anisotropies of the CMB can be seen as residual effects of these primordial interactions. Implications. 1. Cosmic structure and evolution. The interaction between SMF and RVS could drive the formation of large-scale structures by influencing the distribution of matter and energy in the early universe. 1. Alternative inflation mechanism. Instead of a singular rapid inflation event, the ongoing dynamics between SMF and RVS might explain the uniformity and isotropy of the CMB. 1. Revised cosmological model. This interpretation calls for a re-examination of the LCDM model, potentially leading to new insights into dark energy and dark matter. Notably, in the unified theory of U, the concept of dark matter is rendered unnecessary, as the dynamics of the SMF and RVS interactions suffice to explain cosmic phenomena. Comparative analysis. Both theories acknowledge the CMB as a crucial observational cornerstone that provides insights into the early universe. They agree on the presence of uniform radiation with slight anisotropies, serving as a cosmic snapshot. Differences. Origin of the CMB. The traditional view attributes the CMB to the Big Bang and recombination, whereas the unified theory of U attributes it to interactions between the SMF and RVS. Cosmological implications. The traditional view supports the standard model of cosmology, LCDM, including cosmic inflation, dark matter, and dark energy. In contrast, the unified theory of U proposes alternative mechanisms, focusing on SMF and RVS dynamics and eliminating the need for dark matter. Theoretical and observational challenges. Testing the unified theory of U. A major challenge is devising observational tests that can distinguish between the predictions of the traditional view and those of the unified theory of U. This requires novel measurements and interpretations of the CMB's properties and anisotropies. Any new theory must account for the extensive body of data supporting the traditional view, including detailed measurements from missions like COBE, WMAP, and Planck. Conclusion. The traditional view of the CMB as the afterglow of the Big Bang is deeply rooted in modern cosmology, supported by extensive observational evidence. However, the unified theory of U provides a transformative alternative, suggesting that the CMB results from the primordial interactions between the SMF and RVS. This perspective invites us to reconsider established paradigms, offering potentially groundbreaking insights into the nature of the universe. By understanding these early cosmic conditions through the lens of the unified theory of U, we open the door to a deeper and more integrated understanding of our cosmos, challenging the conventional narrative and illuminating new paths of inquiry.